Hi everyone, and welcome to this webinar dedicated to industrial equipment motors. This is part of a larger series of webinars that we are creating, especially dedicated to industrial motors and special applications. So today we are going to discuss about a specific motor that is equipping unmanned aerial vehicles, or UAV, as they are called in short. And we'll have a short introduction, and then discussing about the specific type of motor can be modeled in ANSYS workflow. Then we'll cover the aspects of performance estimation for this type of machines, and concluding with a summary, leaving time for Q&A. So unmanned aerial vehicles, or UAVs, also known as drones, they rely heavily, obviously, on the performance of their electric propulsion system. We can see here a generic image of a quad drone with 4 electric motors. The solution for electric motors to realize the propulsion of UAVs is done typically with brushless permanent magnet machines. And from this class, brushless DC are the standard choice, mainly due to their high power-to-weight ratio, reliability, and efficiency, and they are all critical factors to maximize the flight time and maneuverability of the drone. The motors must deliver precise control or rapid response and thermal stability for this type of application. Obviously, this will make the modeling and design of brushless DC motors for UAVs a multidisciplinary challenge. We'll need to perform a detailed analysis and look at the electromagnetic aspects, the thermal aspects, and the mechanical, all considered together in a multi-physics approach. So during this presentation, we'll go over a quick overview of BLDC motor structure and how they operate, and then we'll see how we model the performance of this type of machine specific for UAVs application. First of all, why we take BLDC? It was already mentioned because of the capabilities and the high performance and high torque and power ratio to volume. But additionally, we will discuss today about outer rotor topology. So it's a specific configuration for BLDC machines. Why that? Because as you can see from the image on the right-hand side of the screen, the outer rotor can be mounted in the propeller of the UAVs, and therefore it will operate more compact in a more compact way. So the stator will be central, and together moving with the propeller of the UAVs. So it's a natural solution for this type of application. Also, an outer rotor typically will deliver higher torque capabilities compared to an inner rotor topology. This is a known fact. The frequency, however, will be slightly higher than comparable to an inner rotor. We will see immediately we are going for a relatively high number of magnetic poles for this application. Axial length is significantly shorter than an equivalent in power and torque in a rotor topology. There are some challenges from the ingress protection. It's relatively complex to close the motor from all sides and to insulate it from getting any impurities coming from the outer environment. Imagine that UAVs will be up in the air, and all sort of particles can penetrate and get into the inside the motor. So therefore, it has to be well protected from outside environment. It's useful to mention that beside the UAV's application, such topologies are very well used and suitable for other high-speed, low-speed and high-torque applications. So we are talking about e-bikes, fans, pumps, or surgical robots. So today we are going to look at the key components of the BLDC motor, how we model this outer rotor topology, how we model this in ANSYS workflow, how we calculate different parameters of the machine. We will look at the elements that are used to model this machine. Typically, we make use of a hybrid approach, combining finite element, 2D or 3D, plus analytical calculations. Also, we are coupling the analysis from the magnetic, thermal, and mechanical point of view so that we can investigate the effects of all the aspects for the high performance of this machine. Brushless DC machines are widely used in power tools mostly, but also they will have a very good capability for UAVs and the application domains that I mentioned earlier. So they are typically, obviously, they will use electronically commutation technique, from where the name of brushless is coming. The supply current of the waveform is trapezoidal or square. Only two phases will be energized during motor operation, and the motor will appear as supplied with quasi-DC current. Hence, we end up with the term BLDC, brushless DC motor, even though this must not be confused with the brushed counterpart of in the motor classification. The main torque ripple component for this type of machine is the cogging torque. And this is essential to be mitigated through various techniques: slots poles combination, profile magnetic poles, or skewing. We'll see immediately what we do in this specific example that we're going to analyze. So let's identify where it's this BLDC topology in the overall class of electrical machines. If we look to this standard classification where we deal with motors and generators, both aspects can be encountered in an electrical machine. Then if we go on the class with DC machines, we can identify, highlighted in a red rectangle, the electronic commutator. So it's a DC machine considered, but with electronic commutation. Otherwise, the permanent magnets in this machine, obviously, they are placed on the rotor, and the rotor can be either inner and outer rotor. Our application, as mentioned, it's outer rotor topology. The stator winding is applied with the DC current pulses, and the rotor field will interact with the energized poles. Basically, we'll have a stator field and rotor field, and their interaction will generate torque. How we can model in ANSYS workflow this type of machines. So the main programs that we'll be using to analyze the performance of these machines are ANSYS MotorCAD and ANSYS Maxwell. In both of them, you can see we can start with the geometry, section, winding, materials. The difference will appear, obviously, in the control and the circuit that is used to define the control of these motors. While in MotorCAD, we have a hard-coded basic electronic circuit used to control of these machines. In Maxwell, we are having full flexibility, and we'll see later on how it works, to create a detailed electronic circuit. Then the performance estimation can be done in MotorCAD, where we deal with multiphysics analysis, looking at electromagnetics, thermal, and mechanical aspects. And there we are having two type of solvers: finite element 2D, that can be either microstatic or transient, time step analysis, and also analytical nonlinear electronic circuit. In Maxwell, we deal mostly with electromagnetic calculation. The model can be done in 2D or 3D using solvers specific finite element, and we deal with the detailed coupled electronic circuit. Making use of MotorCAD or Maxwell, we can optimize the design and investigate the performance of this machine, calibrate it with test data or optimize a certain design. coupling optislang with either MotorCAD or Maxwell. For in-depth physics analysis, obviously, it's possible to investigate further looking in ANSYS Fluent for computational fluid dynamics, ANSYS mechanical structural, and ANSYS sound to investigate noise and vibration, the harshness aspects of the machine. So let's start with an example. So what you see here on the screen, it's a screen capture from ANSYS MotorCAD, geometry section radial view. So we're dealing with a 27 slots, 24 poles topology. So before going into the dimensions that are listed here, so you see there are typical values for the armature lamination, outer diameter between 50 and 200 millimeters. Split ratio between armature inner and outer lamination diameters typically is between 0.65 to 0.75, and some values have been selected. Now the question is why this combination 27 slot 24 poles? You probably realize that this is a multiple of basic combination 9 slot 8 poles. So if you multiply by 3, we'll end up with 27 24. So this machine will have a symmetry of 3. So we can model 1/3 of the machine. But as well, in specific configuration, we can energize only 1/3 of the machine, or if 1/3 of the machine will fail, the other 2/3 will continue operating. This is essential for drones application. So it's always important to select a configuration that will allow the vehicle or the drone to operate, or the motor to keep rotating, even though maybe some failures in some of the coils, possible short circuit, and so on. Here you see some considerations related to the frequency. The rule of thumb is to have a fundamental frequency below 1 kilohertz, and this will allow driving the performance of the machine also with the normal IGBTs, not necessarily to be silicon carbide or other, or natrium gallium technologies. So based on this consideration, we can select a relatively high number of poles, as high as possible. There are some advantages in having more poles. So we can get more torque. The back iron for the rotor and stator can be reduced. And also with this configuration of multiple of 9 slot 8 pole, the cogging torque, which I mentioned earlier, is the main torque ripple component. It's mitigated significantly. So it's not going to be required the usage of skewing or any profiled of the poles for this topology. So we go further, we can look at the specifically to the rotor details. So the template default configuration for this type of machines will typically make use of arc-shaped magnets. In reality, for this machine, we're dealing with rectangular magnets. So they're easier to manufacture, easier to magnetize, and as well, they can be placed on a flat area of the inner surface of the rotor. So how can we achieve this geometry? This can be done in MotorCAD using adaptive template approach. So based on a Python script, it's possible to generate customized geometries in MotorCAD with the advantage of being parameterized and being specific for a certain application. So using this technique, we have generated that type of rotor that is available now on the screen. Other considerations, if you look at the dimensions there for the stator, tooth and back iron, magnet thickness and the width, the air gap width, the question is how do we get these dimensions if we don't have anything available? Well, there are two approaches. Either typically start from what is available on the off-the-shelf existing machines. So taking apart using reverse engineering, one of this configuration, or through optimization using OptiSlang and MotorCAD or Maxwell. For the sake of simplicity and limited in time, we have selected in this case the option of an existing off-the-shelf motor. So what you see here is actually based on an existing configuration. On the axial dimensions, we notice that the dimensions are much shorter. The axial length is much shorter compared to the diameter. It is possible as well to have a slightly longer rotor magnet with a certain overhang. This will allow, on one hand, additional magnetic field linking the stator with the rotor, as well will help with the control of these machines. If you think of the space available on the UAVs, we cannot mount there a resolver or encoder to control to monitor the rotor position for this type of machine. So therefore, the control is going to be done using Hall sensors. And this slight magnet overhang is always useful to provide a clearer mic and is passing the rotor in front of that Hall sensor. Again, helps with the control technique for this type of machines. Here we can see details on the adaptive template. The template geometry has been created using specific features. I mentioned the magnet shape, it's rectangular, and you can notice it's a flat shape for the inner surface area. And this is done using an embedded Python script. Materials. Few points to highlight. So we deal, as in most of other machines, with laminated electric steel, but only for the stator. So the stator in this case is making use of a standard silicon iron non-oriented steel M350-35A. It's 0.35 millimeter thickness standard electrical steel. For the rotor, however, we are going to use a solid steel, magnetic steel material. So in this case, generically defined as mild steel. So it's important to note that for a specific consideration, mainly from the manufacturing point of view and from the mechanical point of view, it's preferred to have a solid magnetic steel. Anticipating a potential question, so how about the core losses in the back iron for this type of machines? Because the rotors are mounted on the surface without the air gap, typically the rotor losses in these machines are neglectable, especially that rotational speed will be only up to 5,000 RPM. So there will be some induced eddy currents in the space between the magnets and just below the magnets sitting on the magnetic steel, but this can be well handled by the structure of the machine. For the axle, we'll use typically aluminum, which is light material, and in here we notice the weights for these components, and we can estimate the bill of materials, and the overall total weight realizes quite light for this type of motor. The winding pattern. This is a fractional slots per pole with ratio there, slots per pole and per phase is 3/8. We are dealing with the tooth wound coils, so each coil will carry, tooth will carry one coil, so the throw of the winding is equal to 1. It's possible to use segmented stator with pre-wounded coils, but it really depends on the size of the drone and the overall application for how long it's required to be up in the air. So in this specific example, we are dealing with a compact stator lamination ensemble on which the coils have been wounded using automatic insertion of the turns per coil. If we look to the distribution, we notice that quite a few number of coils will contain will be placed and be part of the same phase. So we have slots that will carry only phase 1, phase 2, or phase 3. There are some slots with coils coming from 2 phases, but typically we notice it will be a minimal magnetic coupling between phases. We can look as well to the linear pattern, which is useful for manufacturing drawing, and each phase will comprise 9 coils. These 9 coils are grouped in 3 groups, 3 coils times 3. So we're dealing with 3 parallel paths. So I mentioned earlier that it's important to have this parallelization that allows us to operate this machine in case that there is a fault in one of the parallel paths. Obviously, this can be also extrapolated if you think if it's a larger drone. We can have a separate supply for each of the groups, so we can energize 9 slot and 8 pole configuration with one IGBT, a smaller IGBT, another 1/3 with another one. So you'll have typically a 9-phase configuration with 3 times 3, 3 sets of 3-phase configurations. In this situation, however, we deal with only one IGBT, and we deal with 3 parallel paths with 3 coils per path. We can look at the goodness of the winding. This is typical for this machine. So with multiples of 9 slot and 8 pole configuration, notice there are not only odd order harmonics, we deal as well with even order. So this is because in such configuration, the north and south poles do not see exactly the same magnetic paths, and therefore you end up with even order harmonics. Obviously, in a star connection, the multiple of 3 harmonics will be cancelled. So if we look at the same machine, but from the mechanical harmonics point of view, here we notice the harmonic, fundamental harmonic, mechanical one, will correspond to harmonic number 12, which is equivalent to having 24 poles. So we notice that there are mechanical harmonics as well lower than the fundamental. It's what we call subharmonics. These harmonics will not interfere with the immediate performance to generate torque or something like this, but they will appear and have an impact on the noise and vibration. They will impact on what's happening in the machine from the mechanical point of view. So even though the spectrum of harmonics may be quite significant, this because the rotor field doesn't contain the same order of harmonics, the interaction between harmonics of the same order is limited, and in the end the performance of this machine is quite good. Another specific aspect for these motors for UAVs, you notice the copper slot field is relatively low, 0.35. Obviously, this relates to the manufacturing technique, and an optimum wire size can be determined. In this case, we will have used the number of strands in hand, it's equal to 2. And from the insulation in the slot, there is no impregnation for this type of machine normally. And additionally, there is no slot liner either. So what is done in practical production, the stator lamination pack of this is fully coated in resin. So what you see here on the screen, on the image on the right-hand side, a slot liner set to 0.1. It's actually the thickness of the resin that was applied to coat the laminated pack. So we fictitiously model this slot liner in MotorCAD. So then we capture this material, its impact on the thermal performance of the machine. And let's see how do we model the performance of these machines. So in MotorCAD, we make use of this hard-coded electronic circuit. You notice there are two switches and two diodes for each phasing part. We have as well internal resistance for the battery, capacitance filter, and typically what in MotorCAD we are dealing with the so-called hybrid method. So what is done, we have an analytical voltage system with nonlinear equivalent circuit parameters, and these equivalent circuit parameters are predetermined using a finite element. And then we deal with a coupled FEN circuit method, and this we'll see later on is part of what Maxwell solution is. In the hybrid method, these are the settings that typically we will do in ANSYS MotorCAD. So we are dealing with the calculated current types. It's a square wave topology. We have as well a delta connection for this application. We have to calculate and recalculate this each step. We have a back EMF, torque, and self-mutual inductance. These are all calculated in using finite element. And once the calculation is performed, this is what you see on the screen is for one operating point. So we have available different outputs, like in any other electrical machine modeled in the solution provided by MotorCAD and Maxwell. So we have on this example currents and back EMF. We notice one important aspect. Typical BLDC machines, and here is a reference to a webinar that we delivered a few months ago on BLDC for power tools. So those machines typically will have this, will try to have the same shape of the waveform. So square wave currents should go hand in hand with square wave back EMF. This automatically will lead to minimization of the torque ripple. However, a 9-slot A-pole will always generate, or multiple of 9-slot A-pole will always generate quasi-sinusoidal back EMF compared to the square wave current configuration. However, this is something that we can accept even for this application because the torque ripple is minimized by minimizing the Coghlan torque. There will be some extra aspects coming from this interaction between different harmonics of the currents, time harmonics of the current that will lead to some harmonics, respectively, harmonic number 6 and 12 for this type of machine. Then the currents are typically square wave, and we have as well numerical outputs. This is an image of the torque waveform. There is a certain oscillations in the torque waveform, but this is again acceptable for this application. In finite element, we can look as well to the different regions of the machine. We can check what will be the saturation level, both in the stator back iron or in the state or in the rotor back iron, in the stator teeth. And numerical values are available, looking at voltages, voltage component, torque constant, back EMF constant, all losses, torque calculated through different methods, power factor if it's the case, or other aspects related to the machine performance. What else can we do in MotorCAD right now? So we can investigate the torque and power versus speed characteristic. And here we can see the two curves reported on the right-hand side. This is automatically done. We can just, it's useful only to specify the number of points that we want to use to calculate this performance. Again, we can do design of experiments and using a multiple range of parameters variation in MotorCAD and investigate different aspects of the this motor performance. Then I mentioned from the beginning that such design is always important to be multi-physics, like as a matter of fact for any electrical machine design. So we have to consider not only the electromagnetic performance of the motor, but as well the thermal aspects put together. So we'll get losses from the electromagnetic, feed them into the thermal module, and afterwards get a consistent performance with the right temperatures of the different components. Here we see that there is no specific cooling. It's only blown over of the air coming out of, remember that this vehicle will be up in the air. So there is no forced liquid or other specific options. A reminder as well, we don't have any impregnation in this material. The floor liner is actually part of the coating of the stator lamination. So with all this in mind and using MotorCAD thermal module, here we can look at the transient response at this machine. We notice that it's reaching steady state just before the hour. So continuous operation, let's say for less than 1 hour, it's reaching a maximum temperature just above 170 degrees Celsius. This will impose an insulation class for the wires 180 degrees Celsius or H according to the previous standard. So this will ensure that this machine can operate and the drone will be up in the air. Here we notice this calculation is done for about 2 hours. So no component will exceed that temperature. And the hotspot will obviously be in the winding itself. We can see here better in a radial view. So the stator is by far the one where the heat is somehow trapped. It's specific for outer rotor topologies. And most of the losses are located on the stator, so it's not easy to dissipate that heat. A big role it's playing that aluminum axle that it's in the middle of the stator, so it's working like a heat sink for these machines. While the rotor, you notice it's quite happy on the outer of the stator, temperatures around 82 or 80 degrees Celsius. Again, the same fact, we can investigate the temperature distribution in axial direction. And here we can do an extra validation of the thermal performance using a 2D thermal solver to understand where the hotspot for this machine will be. So we notice that, again, the temperature is below 180, so the maximum 171 degrees Celsius. And the conductors placed toward the middle of the slot will experience this higher temperature. It's possible as well to look from the mechanical point of view what's happening due to centrifugal force or a rotational speed of up to 5,000 RPM. And just to validate the fact that such machines, they will operate happily with no problems from the mechanical stress. It's a relatively robust and thick rotor back iron, the cap that keeps the magnets inside the gear guide. So we validate in this way that mechanically, from the centrifugal force point of view, there are no issues. Also, on the mechanical side, we can briefly look at the NVH response for this machine, look at the envelope torque, different operating points. And here, just a screen capture showing things that you can do in MotorCAD, looking at the Campbell diagram to investigate if there are any resonance frequencies between the stator natural frequencies and the rotor frequencies. And in order tracking, we can observe what we can expect from this topology. And this image shows us that theoretically we would expect a a high frequency, resonance frequency, close to 100 decibels, somewhere just below 4,000 revs per minute. However, this machine will typically operate up to 3,000, 3,500. This is mostly the spectrum where it will operate. Other thing we can do with BLDC machines, we can also quickly investigate the efficiency map. And this can be done relying on the equivalence between square wave currents and sine wave currents. And the equivalence is done on the fact that the average torque is determined by the current density. So as long as we use the same current density in a similar model, the same machine, but once applied with square wave, once it's applied with sine wave currents, then the average torque is expected to be similar. What will be different are the losses. So obviously, the square wave current will have a significant time harmonics content that will generate losses. So what we do, we'll see immediately in a diagram. We calculate performance of the machine at different operating points, from minimum speed all the way to maximum speed. And then we'll create a ratio of the losses for each operating point. And this will allow us to estimate this loss variation using specific functions. And this is the performance estimation diagram. We start from the speed as an input. So I mentioned we have a certain operating point between minimum and maximum rotational speed. We do two calculations using the same RMS current. So the calculation is done first in BLDC, which is voltage-driven solution, and where the current is an output. We take the RMS current from there, feed it into the same model, but modeled as a sinusoidally supplied machine. We compare the results, get the loss ratio between them, and with this we feed it into the efficiency map calculation using AC, BLAC, brushless AC configuration topology. And these are the results from the average torque point of view for the same current density. Obviously, there is a slight difference. This is a zoom out graph to emphasize there are some differences. But if you look to the numbers themselves, we are dealing with values below 4%, which is acceptable for the sake of immediate calculation of the efficiency maps for this type of machines. We determine a polynomial function for the loss ratio with speed, stator, rotor, and magnet losses. And they are used in a lab module from MotorCAD that is dedicated to the calculation of efficiency map and duty cycle analysis for electrical machines. Some other settings we need to take into account the difference between square wave and sine wave. When you look at the modulation index, we'll fix the phase advance to be 0. So such machines typically rarely they make use of the phase advance. So we'll keep the current always in Q axis, and then just arranging the amplitude of the current to control the torque. And this is what is achieved from the efficiency point of view: torque on top the top graph, and the power on the lower image on this slide. Now, until now, we looked only in making use of multi-physics approach in MotorCAD. However, we need to validate this performance using a more in-depth calculation, making use of Maxwell. Maxwell will allow us to do finite element analysis in 2D and 3D, and as well coupled to the dedicated circuit. So this is done very easily through exporting. MotorCAD generates automatically a model that is scripted and can be imported directly into Maxwell. So we'll have the same geometry, the same material, the same supply. Additionally, in Maxwell, we need to create a circuit like the one that you can see now on the screen. It's a classical IGBT. So three-phase system. The MOSFETs are controlled with a block that is on the lower right corner of this diagram. So that we can have, in this specific example, a square wave control with the conduction of 120 electrical degrees for each MOSFET in part. And these are the results for the currents on top. And also we see on the branch current that it's reported on the lower side of this diagram. Or if you want, is the current that will flow through the battery. The same calculation it's used to get the results from the voltage point of view. The upper graph is induced voltage, and the torque is reported on the lower graph. If we compare the results, the values obtained with MotorCAD and Maxwell are pretty similar. However, Maxwell will give us more flexibility. We'll be able further to investigate what happens if it's a short circuit. I mentioned the potential fault that one parallel pass will fail. So this can be done with relatively ease in Maxwell to investigate any faults that may occur in performance for these machines. Remember, they need to be continuing operating. So it's not acceptable that a total failure of such a motor, even though we're dealing with minimum 3 motors for a drone or 4 or more. Motor will keep, so it will be quite difficult that the other 3 motors will take over completely if one of the motors will fail. And here we have an animation showing the flux plot for this type of machine in Maxwell. You notice how the magnetization pattern is moving with rotor position. And here we have also an animation from the losses point of view. So the losses will build up in time, so variation with each rotor position, and give us a good indication of where the electromagnetic losses are located in this machine. So in summary, these Outrunner BLDC machines are a preferred solution for drones. We mentioned why are they suitable for this type of application. So they are not too expensive to manufacture, so which is again another very important criteria for manufacturing drones. The system, the motor and power electronics, can be easily modeled in ANSYS workflow. The entire drone actually can be modeled. If you notice, the first slides in this presentation were showing some images using 3D fluid dynamics in modeling in ANSYS workflow, and capturing the entire system, the entire drone. So this is possible as well. So multiphysics, anyway, it's essential for even looking only to the motor itself and the power electronics. The approach that we have described is not unique for UAVs. The same thing can be applied for any Outrunner application with BLDC configuration. And again, we mentioned possible alternatives are e-bikes, pumps, fans, or surgical robots. For ANSYS workflow, we focused on ANSYS MotorCAD and Maxwell. Mentioned OptiSlang, but remember that physics, in-depth physics, can always be done using fluent ANSYS Mechanical and ANSYS Sound. And the link from MotorCAD and Maxwell to the other in-depth numerical methods analysis of this type of machine, it's very straightforward and well established, so you can try to investigate this approach as well.